Okay, so welcome everybody. Today is the third colloquium of the math department for this spring 2020. And the speaker is Alessandro Sisto from ETH in Zurich. And he will be speaking about Gromov Hyperbolicity and beyond. Alessandro was a student here in Pisa. He got his... Okay, so welcome everybody. Today is the third colloquium of there's something strange. I'm spring 2020.
I don't know.
And the speaker is Alessandro Sisto. Okay. Perfect. Okay.
Okay.
I had the YouTube channel switched on. Okay. Now everything is okay. So just 2 words about Alessandro. He was a student here in Pisa. He got his master degree in 2010, and here at the university in Pisa, as well as the diploma from Scuola Normale Superiore. After that, he moved to Oxford, where he got his PhD in 2013 under the supervision of Professor Cornelia Drutu. And since then, he moved to Zurich, where he's still now. And in a few weeks, he's supposed to move to Edinburgh. And his research is about many different topics, but probably the center of his research is geometric group theory. He's probably one of the leading experts in the field of geometric group theory, and his research also uses tools and has applications in related fields like geometry of manifolds, of course, and also non-standard methods for the study of the coarse geometry of groups, and also a bit of probability, since he's also interested in random works on groups. He won in 2018 the Kamel Dushenko Award, and we hope that he will be winning many other awards. Anyway,
thank you.
I think that the talk can start.
Okay, thank you very much for the kind introduction. Thank you very much for inviting me. It's a pleasure to give this talk in this weird circumstances. Of course, I'd rather be there in person, but I hope that we're going to have a good time anyway. Okay, so maybe I should mention that this right part of the screen that's empty for now, it's going to be filled later. It's not a technical issue. And right, so regarding the talk, the title is Gromov Hyperbolicity and Beyond, which is very vague because, to be honest, I wasn't sure exactly what I wanted to tell you about, so to talk about. So maybe let me tell you about the structure of the talk first. So this talk has 3 phases, to use very fashionable terminology these days. So phase 1 is I will tell you about hyperbolic groups. So I will define what a hyperbolic group is going to be one of the central. It's a central notion in geometric group theory, and also a very important notion for this talk. And anyone familiar with basics of geometric group theory can take a nap during this part. I'm not going to say anything that you haven't heard of before. So phase 2 is going to be about my favorite groups. So my favorite groups are mapping class groups. These are groups that appear when you do low-dimensional topology in a multitude of ways. So they're really crucial for topology in dimensions 2, 3, and 4. And they are not hyperbolic group, as I'll mention later. Oh yeah, I should say, so if you're familiar with low-dimensional topology, you can take a nap during phase 2. And mapping class groups are not hyperbolic, but in phase 3, we'll see what we can do about that. So let's say that phase 3 is hyperbolic groups from mapping class groups, and with a question mark. And we'll see why I put the question mark. Okay, so let's get started. Let's jump into it with hyperbolic groups. But I mean, an alternative title for this part of the talk would be a crash course on geometric group theory. So what is geometric group theory? Geometric group theory is the study of groups using geometric methods. And how do we do that? So you can look at actions on metric spaces, but there's one object that we really like, we as geometric group theorists, which is the Kayla graph. So you start from a group, a finitely generated group, and you construct a metric space out of that. And then the metric properties so the hope is that the metric properties of that space are going to tell you something about the group. Very good. So we have a group, and the group is generated by some finite set. And associated to this data, we have the Kayla graph. So the Kayla graph is defined as follows. So K, G, S. It's a graph, so I have to tell you vertices and edges. Let's start from the vertices. The vertex set of the graph is the group itself. And the edges tell you when you can go from a group element to another group element by multiplying on the right by a generator. So edges are of the form G, G, S. For G in G and S in S. Okay, and I promised a metric space, and I defined a graph. So how is a graph a metric space? You can declare that edges have length 1. So declaring edges to have length 1 gives you a metric on a graph, in particular on a Kayla graph. Okay, so that's the definition, and let's draw some examples. Okay, so let's start with G equals Z, and S just the unit. And in this case, the Kayla graph is isometric to R with the standard metric. So it looks like this. There's maybe 0, -1, 1, 2, and so on. And so something that's maybe a bit disappointing is that you have to fix the generating set. So usually, so for Z, okay, you have a, let's say, canonical generating set, but otherwise you usually do not. And if you change the generating set, then you can get kind of a picture which is different. But we'll see what we can do about that. So let me just draw some of the edges here. It's much more messy. It looks something like that. Okay, the local structure is completely different, but maybe you can imagine that this is, it kind of roughly looks like a line. Oh, oops, not G equals to 3, G equals Z, and 2, 3 is S. Okay, so we'll see what we can do about that in a second. But let me draw a couple more pictures. So G equals Z squared. So I saw that the definition of Kayla graph disappeared. So let me bring it up here. Oh, okay, I anticipated a picture. So G equals Z squared as just a basis. You get a grid. And Probably the most important example for this talk, for what's coming afterwards, is if you have a free group. So this is a free group on 2 generators. NS is a basis, then you can. So you see that it looks like this. So I'm not drawing it. I should draw each edge of the same length, but if I did that, I would run out of space very quickly. But I hope you get the idea. So you should imagine that each edge here has length 1. Okay, and let me pull up the pictures. Okay. Are there questions? And by the way, just if you have questions, just ask. I cannot see if you write in the chat or if you raise your hands or anything like that. So just intervene. Yeah, and I'll try my best to answer. Okay. So these are the pictures, and in particular, maybe keep this one in mind and ponder about this one if you haven't pondered about such pictures before. And so, as I said, there's this pesky dependence on the generating set, but it is a fact. So fact, if you pick a different generating set, then what you get out of that is quasi-isometric to the original Kayla graph, quasi-isometric Kayla graphs. So it doesn't matter what quasi-isometric means technically, as long as you remember that it means that it has the same large-scale geometry. So maybe the local geometry is completely different. There's more edges at a point in one graph than in the other graph. But from a large-scale perspective, so if you look at things coarsely, the Kayla graphs have the same geometric properties. That's roughly the idea. So maybe I should give an example with this Z. So in this case, for this Kayla graph of Z, if I remove a point, then I disconnect the space. So removing a point is not, let's say, a coarse operation, but removing a ball is. So if I remove a ball from this space, I get something disconnected. And if I remove a ball from this space, I also get something disconnected. That's kind of the flavor that you should maybe keep in mind. Just thinking large scale, not thinking small scale. Okay. And now we are gonna define first hyperbolic spaces and then hyperbolic groups. So here's the definition. So X, geodesic metric space. And let me pause here before I continue the definition. So if you don't know what a geodesic metric space is, just think of either a metric graph, a graph where you declare each edge to have length 1, or a Riemannian manifold. Okay, and in either case, a geodesic is the shortest path between 2 points, between any two given points. Okay, so geodesic metric space is Gromov hyperbolic or delta hyperbolic or just hyperbolic. I kept Gromov in the title because there's too many notions of hyperbolicity in mathematics. So it's hyperbolic if there exists some constant delta, such that whenever you have a geodesic triangle, so what's a geodesic triangle? It's just given by 3 geodesics, so the shortest paths, pairwise sharing endpoints, so for all geodesic triangle. And now I'm just going to draw a picture. I think it's clearer than if I write everything with formulas. So let's draw a Gdc triangle, like so. You have points x, y, and z. And for every point on one of the sides of this triangle, there exists a point on one of the other two sides which is close to it. Close meaning that the distance is at most delta. So maybe a better picture than this. Okay, let me pull up the definition here. So a better picture than this of a triangle in a hyperbolic space would be something skinnier, something like this. So that's maybe the picture you should keep in mind. So a hyperbolic space is a space where triangles are slim and they look like this. Very good. So examples and non-examples. Example. So non-example R2. Why not? Because you can scale. You can scale triangles. So let's take just an equilateral triangle in R2 and just the midpoint of an edge. And whatever delta you give me, I can scale it up sufficiently much that this point is going to be far from the sides. So R2 is not hyperbolic. So R2 has zero curvature, and this property is supposed to capture negative curvature instead for the differential geometers in the audience. Gonna get back to this, but let's first do a more elementary example, which is the Kayla graph of the free group. Let me try it better. Okay, so why is this? Well, triangles are degenerate in here. So triangles look like this. And you can take delta equals 0. So let me show you, let me try to show you a triangle in here. So maybe here's one side. So it's a very simple one. Okay. So there's only one injective path connecting any 2 points. Okay, so the triangles here are very degenerate. Okay. And another example, maybe a bit more sophisticated one, is hyperbolic end space. Let me write it. Hyperbolic end space. Or more generally, negatively curved, simply connected Riemannian manifolds. So negatively curved meaning that the sectional curvatures are negative. And that's where the name comes from, that hyperbolic space is hyperbolic. Okay. And let's give you some more. Oh, oops, too much. I'm giving away stuff all the time with this summary. It's the first time that I test this system, I should say, because since this talk gets recorded and will be on YouTube forever, I thought it would be a great time to do an experiment. All right. And now this is a hyperbolic space. What is a hyperbolic group? Let me formulate it as a definition / theorem, because I'm going to give equivalent conditions. So the group G is hyperbolic. If any of the following equivalent conditions holds. So 1, G has one hyperbolic Kayla graph. Okay, as you can imagine, hyperbolicity of a group is something to do with the hyperbolicity of the Kayla graphs. But since there's different Kayla graphs, one has to be careful. So is it all Kayla graphs or one Kayla graph that is supposed to be hyperbolic? And the point is that it doesn't matter, because if you have just one hyperbolic Kayla graph, then all of them are. You have to change the constant from one to the other, but for each Kayla graph there is a constant. And point 3, I'm not gonna explain particularly well, but it's just to mention an example. So G acts geometrically on a hyperbolic space. So geometrically, it's a particular type of action by isometries. And maybe you should, just one thing about what geometric actions. So an example of geometric action is if you have a compact Riemannian manifold, then the fundamental group acts on the universal cover geometrically. But yeah. Okay. So what are examples and non-examples of hyperbolic groups? Well, since we started with non-examples before, let's start with non-example again. So non-example Z2. Okay, so you should think that Z2 is really the main non-hyperbolic group. So that's, when you're talking about hyperbolic groups, you don't like Z square at all. So this mirrors the fact that R2 is not hyperbolic, while examples include, let me start from a maybe trivial example, which is not very interesting, which is finite groups. Okay, so finite groups have bounded Kayla graphs, and a bounded space is hyperbolic. However, this notion of hyperbolicity cannot possibly tell you something interesting about this case, because so this, and it fits with the philosophy that that you're looking at a large-scale geometry. This is a large-scale property because of this delta. You have no idea whatsoever what happens on scales below delta, but if you're looking at a phenomenon that happens at scales a billion delta, then then you have a lot of information about it. Like, if you're trying to measure bacteria with a measuring tape, you're not going to succeed. But if your measuring tape is very long and you're trying to measure distances between galaxies, that's plenty good enough. So that's the philosophy of geometric group theory. You're measuring galaxies, you're not measuring bacteria. Okay, but let's move on to the interesting examples. Free groups. Well, let's say the free group on two generators. Well, we have drawn a hyperbolic Kayla graph. It's at 0, with constant equals to 0. And analogous to, the corresponding fact to this example for hyperbolic n space is that fundamental groups of closed hyperbolic manifolds are hyperbolic. But let me, for example, in dimension 2, the fundamental group of any surface of genus at least 2 is hyperbolic. So let's say this fundamental group is hyperbolic. And this you would see from item 3. That's why I included it, even though I am not gonna explain it. Okay. And right, so there would be a lot to say about hyperbolic groups. There's literally more than 1,000 papers on hyperbolic groups. I should say that I don't have a good reason why this property of thin triangles is so fruitful and so important It just so happens that this very simple property captures a lot of the geometry of the main motivating examples, which are trees and hyperbolic spaces. And it turns out that a lot of the things that you can do in those two cases, you can do just using this simple properties about triangles. I don't know why that is, but it turns out it's that's what happens. And okay, so I cannot possibly survey all that is known about hyperbolic groups, but let me mention at least a couple of simple properties that we would probably encounter in an introductory course in geometric group theory. So hyperbolic groups are finitely presentable, so they admit to finite presentations. That's a nice property they have. And they have solvable word problem, which means that if you're given a word in a generating set, there's an algorithm that tells you whether that word represents the trivial element or not. In fact, a pretty fast algorithm that does that. And there's a much deeper result is that if you have presentations of hyperbolic groups, you can determine if those groups are isomorphic. So this is a much deeper theorem that let's say it's work of many people, but let's say it started by Zela. So the original breakthrough was due to Zela. And also hyperbolic groups have been used to solve big conjectures outside of geometric group theory, and more specifically conjectures about hyperbolic tree manifolds. So the virtual Haken and virtual five-ring conjectures were solved using a lot of the theory of hyperbolic groups and also other bits of geometric group theory, which I think was surprising. I'm not sure that 15 years ago some people would have thought that those big conjectures in tree manifold topology were going to be solved using geometric group theory. All right, but in any case, since I understand that I didn't spend much time trying to convince you that this notion is interesting and worth studying, but on the other hand, I would like to go ahead and tell you other things. So let me make an edict. Hyperbolic groups are interesting, and you're gonna have to believe that for the rest of the talk. So one last thing about hyperbolic groups is that despite a lot being known, there's also a lot of there's also several big open questions about them, and one is going to be relevant for the rest of the talk. And so I have to give you a preliminary definition before I ask the question. So a group G is residually something. Let's say residually finite. That's what the conjecture is going to be about. If whenever you have a non-trivial element, an element which is not a trivial element, there exists a quotient of G so such that two things. One, H has this property P that you're considering. So H is P. And phi G is not the trivial element. Okay, so let me read again for the case P of the property being finite. So G is residually finite if whenever you have a non-trivial element, there exists a finite quotient of your group where that element is still non-trivial. So residual finiteness, so the philosophy of residual finiteness is that you can study your group by studying its finite quotients. So it's a very, very well studied and important property. And the question is, or maybe, I don't know if it can be formulated as conjecture, but so I'm not going to formulate it as a conjecture because most people think this is false. So question, are hyperbolic groups residually finite? And to give you an idea for why this question is so important, let's get back to these big conjectures in trimanifold topology. And it was known before they were proven that the positive answer to this question would imply those conjectures. And the way that they were actually proven in the end, the last bit of the puzzle to be completed, was actually proving that enough hyperbolic groups are residually finite for certain things to happen, and in particular the conjectures to be true. Or maybe, so to be more precise for the specialists, I should say the way it was proven is to prove that enough hyperbolic groups are virtually special, hence residually finite. So, but there's other, I mean, that was one of the reasons why this question was of interest to people, but it's still open. So there's a very partial answers to this. So it's yes in very special cases, but I'm not sure that anyone has a candidate counterexample. Or I mean, a candidate counterexample where that can be attacked. Okay, so now it's a good time for questions, since I'm gonna move on to the second part of the talk. So I'm gonna, any questions? Okay. So the second part of the talk is about mapping class groups. Okay, so what are those? Let's start by, since I will have to say it many times, let me set notation for the surface of genus G, or if I want to be precise, the closed, connected, orientable surface of genus G. And well, it's just this. So it looks like this. And to avoid saying false things, let me always take G at least 2. Okay. And what's the mapping class group of this surface? The mapping class group of sigma G is the set of, well, the group of homeomorphisms. Orientation preserving, you can't forget about that. And you consider, but it's not that, you consider two homeomorphisms to be the same if they're homotopic. So up to homotopy or isotopy. It doesn't, so up to deformations, let's say. So two homeomorphisms are the same if you can deform one into the other continuously. And to be a bit more precise, I should say that it's, I mean, I can write it as homeo plus for orientation preserving of sigma G. And I mod out by the subgroup, the normal subgroup of the homeomorphisms that are homotopic or isotopic to the identity. And in this dimension, there's no, so in dimension 2, there's no issues of homeomorphisms versus diffeomorphisms. So you can also change, think about diffeomorphisms instead if you prefer. And okay, so we started from a huge group. This is pretty huge, uncountable. And we mod out by a pretty huge subgroup. It's not clear what happens, but it turns out that you get a finitely generated group out of that. So it's a much smaller, in particular, it's countable. And okay, so this is very commendable, making a group smaller, hence probably more understandable. So, but why care? And there are many reasons for this. I'm gonna explain one reason, one of many, many possible reasons why one should care about the mapping class group. So here's a construction of a tree manifold. So if you take a homeomorphism of sigma g into itself, homeo, then you can form something called the mapping torus. So mapping torus is sigma g times 0, 1. Okay, so you have thickened your surface. So let's say that sigma g times 0, 1 looks something like that. Okay, and what you do is you glue one boundary component to the other using phi. So you identify x0 with phi x1. So it's a very specific construction of a manifold, of a tree manifold. And by the way, the virtual fibering conjecture that I mentioned a few times says that every hyperbolic manifold has a finite sheeted cover, which is of this form. Okay, so what does the mapping class group have to do with all of this? So if you want, the parameter space for this construction is just the set of all homeomorphisms. So it's really big. And there's, with such a huge parameter space, it seems hard to understand this construction. But turns out that if you have homotopic, so if you can deform one homeomorphism into another one, then you get the same manifolds, or homeomorphic manifolds in the end. So the parameter space for this construction is not the set of all homeomorphisms, it's the mapping class group. So it's much smaller, it's much nicer, but you have much more hope of understanding this. And there are many gluing constructions. So when you do topology of manifolds, you do a lot of cut and paste, and this same phenomenon happens for all this kind of cut and paste constructions, that you're gluing various pieces using homeomorphisms of boundary components, for example, and you don't actually care about the specific homeomorphism, you care only about the mapping class, so the homotopic class of that homeomorphism. So for example, another construction that does this is Uyghur Splittings, and so that's interesting because every close connected oriented, I should say, tree manifold has a Uyghur splitting. So there's this construction parameterized by mapping class groups that gives you all tree manifolds. So this and from mapping Torah, you see that if you, so the hope at least is that if you understand the mapping class group, you understand tree manifolds, roughly. And I'll give you an example of a result of this type, that you know something about mapping class groups and you deduce something about tree manifolds. And in general, whenever you study the mapping class group, you have a secret hope of proving something about tree manifolds, or often at least. But I mean, I personally like it very much just as an object of study in itself. I find it very fascinating and interesting. Okay, I should tell you more about elements of the mapping class group. So now we just have a definition. So let me. So the next section is important mapping classes. So elements of the mapping class group are called mapping classes. So a mapping class is just a homeomorphism considered up to homotopy. So important mapping classes are Dane twists. Okay. So let me explain a Dane twist on an annulus first. So let's start from A, an annulus, which is just circle times 0, 1. And it looks like this. And the best way to understand well, a good way to understand the Dane twist, which is of the annulus, which is a self-homeomorphism of the annulus, is to look at what happens to a specific arc, which I'm going to draw red. So here's the arc connecting the two boundary components. And what happens to that as you twist is that it gets mapped to this. Okay. So with this in mind, what's the formula? So let's say that S1 is parameterized by an angle. Then I'm gonna rotate more and more as I go from the inner boundary component to the outer boundary component, until when I get to t equals 1, to the outer component, I've turned all the way to 2 pi. Okay. So it's this funny self-homeomorphism of an annulus, so a Dane twist on an annulus. And what happens instead on a general surface? So you start from gamma, a simple closed curve on your surface. So maybe it looks something like this. So here's your surface. And here is gamma. Okay, and you make an annulus around gamma. So you can call it A if you want. So you look at the regular neighborhood of gamma. And the Dane twist associated to this curve is the identity on the complement of the annulus. Okay, so here. And just the Dane twist on the annulus. Okay. And turns out that the mapping class, so I'm being slightly imprecise here, I mean the mapping class corresponding to this homeomorphism, and the mapping class doesn't depend on the various choices that we made, like the annulus, and also the homotopy class, like gamma within its homotopy class. But let's not get into this too much. So here are some interesting elements of the mapping class group. Turns out that they're infinite order elements. It's not completely trivial, but it's true. And I mean, you can imagine that there's more and more twisting, so it's never, so no power of this can possibly be homotopic to the identity, and that is correct. And also another interesting thing is that the fact the mapping class group is generated by Dane twists. In fact, finitely many. So it's a finitely many Dane twists. It's time to pull up this. And so regarding this philosophy that when you prove something about the mapping class group, you should wonder whether you've actually also proven something about tree manifolds. So the fact is, this fact turns out to imply that every, well, I should say close connected oriented. So let's say the standard hypothesis to do topology of manifolds, or most of topology of manifolds is done under this hypothesis. Okay, maybe that's excessive. I'll take that statement back. A lot of it. Anyway, every close connected oriented tree manifold is the boundary of a compact four manifold. Okay, so I'm not going to explain to you why the fact implies this, but it's just to, to give you a hint that there are very deep connections between mapping class groups and manifolds, and tree manifolds, and in this case even four manifolds. Okay, so we talked about hyperbolic groups, we talked about mapping class groups, and now another fact about the mapping class group is that it is not hyperbolic. So it does not fit in this framework that I introduced in the first part of the talk. So what's the reason for this? So the reason for this is that if you have gamma and alpha, so one reason for this, I should say. So since we talked about Dane twists, a reason related to Dane twists is that if you have two simple closed curves that are disjoint, disjoint and not homotopic, then they generate a subgroup of the mapping class group. So you can see easily that they commute, okay, because they have, they do, their supports are disjoint. They do something on different parts of the manifold, so they commute. And then this gives you a z square. Okay, let me maybe. So for example, if you do Dane twists around here and around here, then they will commute. So say it is come and generate a z square. And z squares are forbidden in hyperbolic groups. Hyperbolic groups do not contain z squares. I guess it's easy to believe in, though it's surprisingly not real fact to prove. But it's very believable, and it's true that hyperbolic groups do not contain z squares. So this fact right here tells you that the mapping class group is not hyperbolic. Mapping class groups are not hyperbolic. And it's even worse. You can make other z squares. So more generally, let me now maybe add one genus to have more space. More generally, if you have two disjoint surfaces and you have some homeomorphism that only act on, so two homeomorphism each acting on one of these two, then this also will commute. And if they're of infinite order, they will also give you a z square. So you can make also other types of z squares. Okay. Okay. So we like mapping class groups. We like hyperbolic groups. They're not hyperbolic. So let me give tantalizing title for the last part of the talk, which is making MCG sigma hyperbolic, sigma G hyperbolic. What do I mean by that? So the rough idea is, okay, we have all these z squares that we don't like. But why don't we take a quotient or quotients? So this part will be about quotients of mapping class groups. So I take these quotients where all these obvious z squares that I see are finite. They become finite. So this, let's say, obvious abstraction to hyperbolicity that I had disappears in these quotients. So there's a hope that these quotients are, in fact, hyperbolic. Okay, so it's a rough idea to make hyperbolic quotients of mapping class groups. And turns out to make it work, you need some reasonably heavy machinery. Let me write it as a fact. So mapping class groups are examples of, so they're not hyperbolic, but they are what's called hierarchically hyperbolic. So it's a hierarchically hyperbolic group or space. So, and from now on, I will abbreviate this to HHS. S stands for space. Okay, and I will not explain to you the definition, even though if I have time, probably will not have time at the end to explain to you, let's say, the most important part of the definition. But I certainly cannot explain to you the whole definition because I have it right here. Okay, so here is the definition of hierarchical hyperbolic space. Starts properties 1, 2, 3, 4, 5, 6, 7, 8, 9. So it's a notion. It's a bit of a complicated notion that we introduced a few years back with Jason Berstock and Mark Hagan, and it encodes. So it roughly encodes all the non-hyperbolicity of the mapping class group into something that you can then control. But okay, that's maybe not great, but do not despair. You only need to know exactly 2 things about hierarchical hyperbolicity for the purposes of this talk. Just 2. And I'm gonna tell them to you just now. So what you need to know, and it's really very little. So one is that when you have a hierarchical hyperbolic space, then it has a complexity. So, and the higher complexity, the more types of z squares you can make in there is the idea. And if you have something of low complexity, so complexity equals 1, implies that this space is hyperbolic, or this group is hyperbolic. There's a parallel theory for groups and spaces. That's it. So if you just please allow me to use these 2, and forget that you saw this terrible long definition. Okay, with this in mind, what can we do? So how do we implement this idea here? Well, it seems so. Let's first start from the z squares generated by Dane twist. So how do we make this finite? Well, we could mod out by the subgroup of the mapping class group generated by Dane twist. That's not a great idea because we will get the trivial group. I told you that Dane twist generate the mapping class group. So maybe we can try with powers. So which leads to considering this subgroup, let's DTK. So this is the subgroup generated by all k powers of Dane twist. The normal subgroup generated by all k powers of Dane twist. And okay. And let's see what happens. So maybe we don't expect this already to be hyperbolic. We're just modeling this out, but we expect that the situation improves, and indeed it does. And okay, I will write some quantifiers in a second about the k, but mcg sigma g mod dtk is HHS of strictly lower complexity. So how do you interpret this? It's one step closer to being hyperbolic than the mapping class group was. The quantifiers are that k has to be not quite that k has to be large. It's a little slightly more technical than that. So there exists k0 so that for all multiples, non-zero, I should say. So multiples. Okay, but just think of it as large. So if you model large powers of the twist, you get something that's one step closer to being hyperbolic. Okay, not just that. Like I'm not gonna go in that direction, but yes.
One question. An integer.
Oh yeah. Sorry, I forgot to mention. Yes, complexity is an integer. Yes.
Thanks.
Sure. Yeah, I wanted to mention it, but I forgot. Thank you. So okay, you might be interested in these questions of the mapping class group for different reasons. So they kind of show up when. Also, I don't know anything about that, I should say, but they kind of show up when you look at quantum representations. There's other people in the audience, I think, that would know more about that than me. And this theorem tells you, gives you access to a certain library of results about hierarchical hyperbolic spaces. So you know that they have, the quadratic name function, solvable word problem, finite asymptotic dimension, uniform exponential growth, all sorts of things. But for the purposes of this talk, let me just say that they are one step closer to being hyperbolic than the mapping class group was. And okay, so the idea is that this is just so another idea. So this was just the first step, and you want to take further portions because you preserved the whole structure that you had before using this hierarchical hyperbolicity, and so you can try to do something similar again. And there is a way to iterate this. So let me. So same set of authors. Let me state separately the case of the genus 2 surface. So mapping class group of the genus 2 surface is residually infinite hyperbolic. So let me put the parentheses, so maybe I put a dash, infinite hyperbolic. Like more the parentheses. So I'm not sure that this property is interesting in itself, that every non-trivial element maps non-trivially to an infinite hyperbolic quotient. But so this is a way, take it as a way of saying that not only you construct one quotient, one hyperbolic quotient, you construct many, and you have flexibility. We'll see that this flexibility also helps to engineer quotients of different types. Okay, and and for those of you who know what that means, it's actually fully residually infinite hyperbolic. Okay, let me write the general case. MCG of sigma g is also residually infinite hyperbolic. But there's a big if. So big if all hyperbolic groups are residually finite. So why does this have anything to do whatsoever with this taking quotients of mapping-plus groups? So the thing is, for the first quotient, you have Dane twist, they generate some z's, and you kill some powers of the Dane twist. At the further quotients, what you want to kill, so what you want to make finite are certain hyperbolic groups, and you want to make them finite by modding out by finite index subgroup of them. But maybe you don't have a finite index subgroup of them. So we don't have any additional insight on the residual finiteness of the hyperbolic groups that are involved in the construction, in this construction. So I'm just going to state it like this. If all hyperbolic groups are residually finite, but it's really, you don't quite need the full power of that. You need certain specific hyperbolic groups that you encounter during the construction. And now there's two ways to start from this theorem and explore. So let's say there's one which is, let's say, the virtual Haken type direction, like mirroring what happened with the virtual Haken conjecture, which is, okay, let's now find a class of hyperbolic groups which we can prove that are residually finite, and let's remove this big if from the theorem. In the other direction, instead, and I have no idea which direction is the right one. I mean, you wouldn't call it, otherwise you wouldn't call it research. So let me ask the question. So do all mapping class groups have infinite hyperbolic quotients? So if you can prove somehow that the mapping class group of the genus 17 surface doesn't have any infinite hyperbolic quotient, then there must be some non-residually finite hyperbolic group somewhere. And then you've answered this long-standing question about hyperbolic groups. So how much time do I have? Not much, right?
Yeah, I think it's almost over, basically.
Okay, so let's see, okay, so I'll just mention the other results I have, let's say, as a slide for that, so they're a bit more technical. So there are further questions on, so whatever these two questions are, they're questions about finite index, about finite quotients of mapping class groups, rather refined questions that came up in other people's work. In particular, this question, this question 3, is related to profinite rigidity of three manifold groups. So, which is basically asking the question: can you tell a group from its finite quotients? It's a very hard question, and in their work, Bratson, Reed, and Wilton have encountered, stumbled upon this property of mapping class groups, or finite quotients of mapping class groups that would help for in the direction of residual finiteness, of profinite rigidity for three manifold groups. So I'm not gonna say what this means. There are questions about finite quotients of mapping class groups. And again, if all hyperbolic groups are residually finite, then the answers, then yes, then these questions can be answered. So there's this surprisingly, there are even more connections between the structures of finite quotients of hyperbolic groups and finite quotients of mapping class groups than the theorem. But okay, so this was more technical, just to say that there's more. And also you have to exploit the flexibility of the construction to say yes to those. And yeah, so let me end by mentioning no to either of these questions. Question 1, question 2, or question 3 implies that there exists a non-residually finite hyperbolic group. So maybe you want to look into this question or give us further insight on residual finiteness of the hyperbolic groups that need to be residually finite for our construction to work. Okay, and I'm out of time, so I should stop here. Thank you.
Okay, thanks a lot, Alessandro, for this talk. And are there any questions or remarks or suggestions for the last questions?
Answers, possibly.
Yeah. You
I
just
have a question.
Okay. Go on.
Hello, Alessandro. I'm Ludovico.
Hi.
First of all, thank you very much for the seminar. It was interesting.
Very
I have a question, but I don't know if it is interesting. I mean, is there any example of a single group, an explicit group, which we know that it is a hyperbolic, but we don't know if it is residually finite?
Yes. So you're welcome, first of all, and thanks for the question. So there are examples of hyperbolic groups that do not embed into GLN. So embedding into a matrix group is a way to show that the group is residually finite, and there are hyperbolic groups that are known not to embed, and so I guess residual finiteness of those is open. So the way you construct them is you start from lattice in which rank 1 Lie group works. I guess quaternionic, and you mod out by a large power of some element. So there's a construction. There's a.
Okay, it is perfect for me. Thank you very much.
Sure.
Francesco had a question, right?
Yeah, hi. So thanks for the talk. And so I wanted to know if the mapping class group is residually finite.
Oh, yeah. Yes, it is.
Okay, yeah.
So which is why I was careful saying residually infinite hyperbolic, because, since finite groups are hyperbolic, then
right, yeah,
you could have used that. Yeah, so it is residually finite, yes.
Yeah, anyway, you cannot reach Z, right? With this thing, or can you?
Right. Yeah. So like you can write non-elementary hyperbolic rather than infinite.
Okay. Yeah.
You cannot get any virtually Z group.
Okay. Yeah. And another question that I had is, what is special about 2? Why can you like?
Right. So the thing is, for 2, we know enough hyperbolic groups that are residually finite. So at the because at the second step of after you model Bedin twist, the next thing that you will want to model turns out that they are small constellation groups, and then yeah, exactly. So that's the reason why we can get to 2, but then the next one already we don't know what kind of groups you encounter. Well, I mean, whether they fit into any known class of residually finite hyperbolic groups, or if there's some, I mean, maybe for the genus 3 surface you can do it by hand. I don't know. We didn't try.
Yeah. All right. Thank you.
Sure.
Alessandro, I saw in the question by Reed and Brightson and the notion of omnipotent.
Yes.
What does that mean?
So basically that you can prescribe slightly weaker than that. So you can prescribe, take a step back. You take 2 independent pseudonosovs, and you want a finite quotient where those pseudonosovs have prescribed order. It's not quite that, it's the ratio of the orders. So you want to be able to prescribe the ratio of the orders of images of 2 given pseudonosovs in the quotient.
Thanks.
Are
there other questions?
Not I'm gonna. But so one thing that I'm gonna give an answer to a question that hasn't been asked. So I just wanted to, so maybe you don't care, you probably don't care, but I'm very happy about this. So you remember this very, very long definition of hierarchical hyperbolicity. So one of the main things that we use to prove these theorems that I showed you is that now there is this criterion. So whatever this says, like, it's just visually very nice and short, and I'm very happy about it. That's okay. And you can go and prove that all your favorite groups are hierarchically hyperbolic using this. Don't read the original definition.
Okay. Thanks for the good news, and thanks for the talk. And so I would like to thank also everybody who came to listen to our colloquium. And goodbye, and see you next time. Thanks to everybody.
Thank you all for tuning in on my behalf as well.
Okay. Bye.